Well, welcome Earth Space Sciences class. This is attempt number 2 at this video. It turns out computers actually do need electricity, and you do need to charge their battery periodically. Oops. So anyway, yeah, coming you from quarantine. My brother tested positive, even though he has no symptoms. But given when he tested positive, that puts me in quarantine until December 7th. So I have no symptoms. Yeah, here we go. So we're going to try, as my email said, I'm going to try to make 1 or 2 recordings. 20 to 30 minutes is my goal for Tuesday, and then again 1 or 2 for Thursday. My hope is to cover lecture material online, and I'll look for questions for you in emails. But then to do as many of the activities next week and a little bit of lecturing as time allows. I want to also try to leave some time to help you with rock mineral identification. I want to remind you not to forget to complete the plate tectonics and the earthquakes labs. I have included the plate tectonics diagrams that I wanted you to fill out. If you've lost yours, there are some on Moodle. I've not gotten the earthquake ones on there yet. I'll see if I can. But at any rate, don't forget those, and you can email them to me. Some of you have, some of you need to complete a few things. But yeah, that's in the short term what I'm hoping to do. Yeah, I just got the word yesterday late, so I'm scrambling myself to try to make this class what it should be. So this will be an attempt at that. So at any rate, last time I believe we left off with consideration of our solar system. And this is a diagram of our solar system. And, like many diagrams, it has its flaws. It's a very nice image. It illustrates sort of arrangements and gives you a rough idea of size, but it's not accurate. I want to pause. I want you to pause right now, and I'm going to include on Moodle a link to another group of people's attempt to scale the universe. If you remember the solar system. If you remember last Tuesday, we tried to do that in class in 2 different ways. One, reducing the size of the planets and their distance from the sun down by the same factor. And when we did that, we couldn't keep the planets visible and even in the building. Which would be very valuable for an elementary class. Then the second attempt, we reduced the size of the planets and the sun by 1 factor, and we reduced their distance from the sun by another factor. We were able to keep it in the universe, yeah, in the universe, able to keep it in the classroom, but it had that one shortcoming, that we weren't using the same factor. So this video that I want you to watch is a gentleman's group's attempt to scale the universe using a large flat area in California, some good math, and a fair amount of time. And I think it's about 7 minutes long, and I think you will enjoy the video, and I think it's quite informative. So I'll pause here, or have you pause this video, go watch that one. Again, the link to it is in Moodle, and then come back, and we'll pick it up from there. Okay, assuming that you did that, to make the point that this is not to scale, I've got another image that I want to show you. Here is one person's attempt. See if I can zoom this up just a little bit more. That's good. So here are we call them the inner planets. The planets closest to the sun in our solar system, Earth and Venus, which are termed sister planets because they're similar in size, but that's where the similarities end, because Venus is nothing like Earth. Thankfully, Earth is nothing like Venus. And here is Mars, okay, much smaller, and Mercury. And this is old enough that it even has Pluto in it. So you can see comparatively the size of those planets. And then if we throw in all of the planets in our solar system, there we have Jupiter, Saturn, Uranus, Neptune. And we have then also the 4 inner planets still listed down here and shown down here. And you can see the difference in size, how much larger, in fact, Jupiter actually is. We kick it up one more notch. Let's throw in the sun. And now in this image, there's the sun. Here's Jupiter. And the smaller inner planets plus Pluto Actually, Pluto is not this one right here. Pluto is a little dot that you can't even hardly see down here. Because these would be the four. This would be Earth, Venus, Mars, and Mercury, and Pluto's just a tiny speck down here. So that's how big they are compared to the Sun. And let's see, I need to move this up and out of the way a little bit here. And then if we take it up, this is something I'm going to come back to later just to give you an idea for how big astronomical features actually are. So take a good look at our Sun and our planets, okay? Okay, here's some other stars. Now here's our Sun. Jupiter is 1 pixel, as it says here. You can't even see Earth. Here's Arcturus. Okay, here's Sirius. I'm serious. Brightest star in the night sky. It's the eye star in the dog constellation Canis. Okay, so we can do better than this, folks. I'm not done yet. So look at the Sun now. Let's go up one more crack. Here is Betelgeuse, one of the largest stars that we know of. It's one that's in the constellation Orion. The Sun has been reduced to 1 pixel. Can't even see it. Here's Sirius, the brightest star in the night sky. These are from the previous page. Rigel, Aldebaran, Betelgeuse, and Antares. Look at the size of those things. We'll talk a little bit more about that later. Anyway, just take a good look at that, and I'll scroll back down through to our Sun. And oh my word, how big some of those other features are. Okay, to make a case for why Pluto is not in the Planet Club, I want to put this illustration up, and it's an old image, but it has usefulness. I need to shrink this down just a little bit so you can see it all a little bit better. Okay, these are the orbital paths. Now it shows them as circles, and we know they're ellipses, so you got to kind of just take that with a grain of salt. But the orbital paths of most of the planets are very similar. Okay, that's probably the best takeaway here, except Pluto. So this is Pluto's orbital path, and you can see Pluto actually is not the farthest planet from the Sun in a portion of its orbital path. Neptune is, because Pluto actually moves inside of Neptune's path. Just so you know, so here's Mars, and here's the inner planets in here, so you know how long those paths are. Earth's orbital path is like, what is it, 584 million miles long. So, you know, these are tremendously long paths. But this is just another bullet, if you will, a nail in the coffin for Pluto, why it's not considered a part of the Planet Club, if you will. So if you look at your notes, you see there are 3 criteria generally for a planet, and that is that they orbit the Sun. Of course, Pluto does that. That they're large enough for their own gravity to make them round, and that's true. I mean, these images are just images, but they're round. Okay, and that they've cleared their neighborhood of small objects. It means, remember, gravity, one of the forces that determines where matter is in the universe, that attractive force that pulls everything into it. Because planets are large and they have a substantial gravity, as they've moved around their orbital path, they have sucked into them much of the debris that's along that orbital path, or their neighborhood in the jargon of this. So if they have cleared their neighborhood of, you know, significant debris, that will be the 3rd criteria for a planet. Well, we have this other group of planets, and my computer crashed here a little bit ago, so I want to open up, another image for you. Trans-Neptunian objects, that's what we're after. And yeah, that's a good one right there. There we go. Open image in a new tab. Bada bing, bada bang. There we go. That's too big. Okay, so this gives you an idea of, that's pretty good. Some of the other objects that are out there. So here we have Pluto, okay? But these other objects are scattered through space in various places, closer to, well, if I go back here, if we look here, here's the asteroid belt, there's Ceres, here's Pluto, Makemake, here's Kuiper belt objects, here's Eris up here. And so if I go back to, so again, Eris, Pluto, Makemake, love saying that, Ceres. So you can see they're spread out in different places in our solar system. But if you collectively look at those other objects, which we're going to call dwarf planets, here's a collection of some that we know of. And they're pretty round, many of them. Not all of them are, but many of them are pretty round. And there's some of them are in the asteroid belt between Mars and Jupiter. Some of them are in the Kuiper belt, which is a similar structure out farther, though, beyond Pluto, and scattered other places. So we call these dwarf planets. A dwarf planet has the same features, for the most part, as a regular planet does. They're round. They orbit the sun for the most part. They're around. They orbit the sun. But there are two last features here, and one is that they're not a satellite. That means they're not a moon of another planet. If they're a dwarf planet, they can't be a moon of another planet. And if they're a dwarf planet, they've not cleared their neighborhood of other space debris. Okay, so that's what makes a dwarf planet and distinguishes them from regular planets. So if we go back to this illustration here, I kind of like this one. There are the association that we saw when we did the activities with scaling our solar system, modeling our solar system. We have here what we call the 4 inner planets and the 4 outer planets. These 4 inner planets aren't just inner planets for no reason. They share similar characteristics. And if you look at your notes, you'll see they're denser, they're faster moving, they tend to be rocky. We call them the terrestrial planets. Okay. Normally at this point then, if we shift then to a consideration of these outer 4 here, I ask people what is their perception of what it would be like to stand on the surface of Jupiter or any of these planets, but I pick on Jupiter because it's the biggest one. You know, and that's something that I would get a range of responses, and you would in an elementary class what it would be like. The truth of the matter is that Jupiter's surface is not a hard feature. You would just sink into the core, toward the core of Jupiter, until you were crushed by the gravity of the overlying material on you. Jupiter's surface is not solid. It's believed not to be solid, since we've not ever been there. Been close, but not been on it. Yeah, so its density is a little different. It's very large still. It has a lot of mass, but it's not got a solid surface. And so similarly for these other 4 planets, we call them the Jovian planets. And they're slower moving, they're less dense, and if you look, they're going around the sun too, but they're gaseous. I guess that goes along with less dense. And so, yeah, we have that distribution of planets. There might be a 9th planet right here if all the material in the asteroid belt coalesced into another planet. You know, some people say that would be enough to make a 9th planet. All these planets are moving counterclockwise around the sun. So they're all moving in roughly the same direction. So moving like this, counterclockwise around the sun. So all these planets moving like so. Okay. Now at this point, I would take one of my globes and that I have in class that I'm also proud of, and I would hold up a sun, and this is maybe an illustration I'll try to remember to do. I'd hold up a sun, and I would move the globe counterclockwise around the sun. Okay, but it's important to notice that that's if we view our solar system from the north side, looking down on it from the north side. And north would be defined based on Earth's position, okay? So, and Earth's path. So, if we look at the sun and the Earth from above, from the north side, yep, the Earth and the planets are going counterclockwise around the sun. But if I switch that around, trying to keep it go the same direction, if we look at it from the south side, what was counterclockwise becomes clockwise. All that to say that it's important to describe the position you are viewing anything from, and in particularly astronomical features from, because it can change one's perspective, and I'll try to demonstrate that when we get into class. Let's see, where am I at? Oh yeah, so you're going to be elementary teachers, and if you think about terms that can be confusing, Certainly, rotate and revolve would be. They both start with R. Not only that, if you've got little kids in your class that like westerns, and they like to have that 6-shooter on the side, another name for that 6-shooter is a revolver. But if you think about it, the cylinder actually rotates, and so the confusion abounds. And if you look in your notes, to rotate is turning about an axis through a body's center. So if I had my globe here, and if I could bring it into quarantine with me, I would spin it, and that globe would be an example of a rotation, of rotating. It's spinning around the center of rotation. To revolve would be to take that globe like I was doing just a little bit ago, hold the sun, and take that globe and move it around the sun, trying to illustrate the orbit of the planets. Okay, that's to revolve. Confusing, potentially. It would be okay to substitute a couple of other words that are just fine. You don't sacrifice any specific detail or anything. But instead of rotate, we could use the word spin. And instead of revolve, we could use the word orbit. And they might be less confusing. Always look for ways to reduce the confusion if you can, particularly in an elementary classroom. Okay, let me just look at my images here, make sure I'm not forgetting one that I wanted to bring up. That's good, that's good. We'll come back to that one. Okay, very good. Okay, so we're going to shift gears here just a little bit, and we're going to move to a consideration of the sun. Okay, right here, the sun. Our favorite star. The sun, in actuality, unlike you see in this picture here, is about 93 million miles away from Earth. Now, you think about that. 93 million is the distance Earth is from the sun, but we've got all these other features. Not only that, but we've got some other features outside of our solar system that we're interested in. And these numbers can get exorbitantly large. And so, actually, let me pull up another image here, and I think it will make the point. I'm going to pull up the image of Voyager 1, and I don't want NASA. Actually, I do want Wikipedia on this one because they have an image that I know that I want. Okay, so here's Voyager 1. This was launched in 1977, just to give you an idea for how big our solar system is. It was and continues to move away from our Earth at 42,000 miles an hour, and so basically it's covering about 1 million miles a day since 1977. Voyager 1 traveled for 35 years at 1 million miles a day before it exited our solar system, if you can imagine that. Again, about 1 million miles a day, 42,000 roughly, 42,000, 44,000 miles an hour, 1 million miles a day of every week, of every month, of every year, for 35 years, moving away from Earth before it got out of our solar system. Folks, when I say that and show you a picture of this picture doesn't come close to illustrating the amount of distance that our solar system covers. Again, that's a long 35. So how would you define out of our solar system? And there's ways they do when light atoms aren't pulled back towards the sun but wander aimlessly, that sort of a thing, kind of like we talked about with the solar system. But so there's Voyager 1, and it's still sending back information, believe it or not. It's pretty cool. It's in outer space, out there. It's not outer space, it's out of our solar system. I wonder what it sees. Well, we can get some ideas. Now, what would you put on that that satellite? Now, people were thinking about that. What do you put on it in case it meets extraterrestrials? Well, they put a gold record on it, and that I'm going to scroll through some of these. So it's got a nuclear power supply that will last for a few more years. So Voyager 1 will continue to go. Voyager 2 recently left our solar system as well. So we've got two satellites out there in space. So here's a picture of them putting the gold record on it in case it's found by extraterrestrials. Let's That was a shot of it going off. There's some of the images it's sent back from some of the planets. Incredible imagery it's sent back. It's really been a real asset. Bear with me, I should have had this already up, but I wanted to show you. There it is. What would you put on that record? You know, if you had to make some choices about sounds of Earth. Okay, so if I go back to this page, go down to the bottom, I think it was down at the bottom, there's a list of things. The disc carries photos of Earth, range of scientific information, spoken greetings from Secretary General of the UN, United States, medley of sounds of the Earth, crying baby, whales, waves, all this sort of thing. It says, and then musical pieces by Mozart, Blind Willie Johnson, Chuck Berry, and somebody whose name I can't pronounce. Kind of interesting mix of people. Blind Willie Johnson and Chuck Berry, yeah. So anyway, that's Voyager 1. And that hopefully gives you some perspective on how big our solar system is. It is a big house. Okay, so again, to go back to what we were talking about with our solar system. It's 93 million miles from the Earth to the Sun. That's a long, long ways. So what do you do about that? Well, you know, if you're dealing with the mathematics of it, much like how much does a proton weigh, well, scientists, remember, they developed the AMU, the atomic mass unit, to make units a little bit easier to deal with mathematically. Similarly, astronomers have done that with the great distances that are involved. And one of the two terms that they've come up with is called the AU, the astronomical unit. An astronomical unit is the distance it is from Earth to the Sun. That's 93 million miles. Okay, so 1 AU is that distance. So now we will measure things in space as 2 AUs, 3 AUs, 4 AUs. It's a new measuring device, if you will, to make it more convenient to deal with the great, tremendous distances involved in our solar system. Okay, so what I think I'm going to do right now is I'm going to pause and publish this video, and then I'm going to produce another one that deals just with the sun, some features that I want you to pay attention to with the sun. Normally, normally we would be doing an activity here, which we'll put off till next week, because we're going to be dealing with eclipses, and we would make a device that would allow you to view an eclipse. So that's coming, and yeah, I'll pause it here, and be sure to go look at that video that I'll post on Moodle.